Okay, I want to say one thing about the last homework that's coming around. I'm sure some of you guys are thinking, wow, I've done all 5 homeworks, I've got full credit on them, and I know that one of the grades is going to be dropped. I guess I don't have to do this one, right? And no, that's the wrong model. That's why I'm saying it. That is the wrong way to think about the homework. You are correct that if you've done all your homework so far, this one, your homework grade is set. This one is not going to affect your homework grade, but it's definitely going to affect how you do on the final exam. Okay, the impact of all of those homework assignments is not so much the small increment that each assignment has in your overall homework grade, which again has a small impact on your course grade. The homeworks matter because that's how you practice solving the kind of problems that you're going to have to solve on the final exam. Okay, so what can I say? You'd be nuts not to do this homework. Do it. It's also the second question. Well, let me back up and say something about kind of a direction I've moved in the last 2 homeworks. I think it was the second question on the homework you turned into the day, the one about choosing a candidate. That story was a little harder to parse than some of the other stories. And one of your assignments, one of your questions on this assignment is also going to be a little bit harder to parse. Just the process of going from the scenario to figuring out, okay, so what kind of game does this mean? How do I set up the payoffs? It's looking a little bit harder because that's where we're at in the class. Okay? One of the skills that you can't underestimate that we're trying to learn in this class is the ability to go from that kind of unorganized, informal description of reality, that's the way we talk about and read about the world we live in, to something that is organized into a game where the assumptions are clear and the logic can be spelled out. Okay, so if you find yourself spending more time just figuring out how to approach that second problem, that's appropriate. It's a little bit harder, but I think you guys are ready for it. Okay. Okay, so last week we did a lot of, yeah, Elaine. Let me look. Elaine is asking how prepared you are to do the homework, and that's actually a good question. Okay, the first question on the homework is actually a pretty easy one. It's just a little warm-up. You were prepared to do this at the end of last week. And if you think you're not prepared to do it and you haven't looked at the lecture notes, some of the stuff that I put in the lecture notes but didn't go over explicitly in class will also help you with this problem. So yeah, that problem, you're good to go on. And I think that by the end of class today, you can at least get started on problem 2. Okay. If you remind me at the end of the class, I'll revisit that. But certainly the thing I was just talking about now, the setting that up as a problem, trying to figure out, okay, what kind of game are we even talking about here, you can do that right now as well. Okay, so somewhere I had some notes. All right, so the main thing we did last week was kind of a prelude to thinking about the repeated prisoner's dilemma. We talked about one kind of repeated prisoner's dilemma where we couldn't get cooperation, and that was the case where the prisoner's dilemma was repeated for a fixed and certain number of times. We saw that the shadow of the future undermined cooperation in the known last period, and the fact that the last period was known in advance undermined cooperation in all the previous periods. Okay, so if we have a clear and definite time horizon in an interaction that is got the form of a cooperation problem, a prisoner's dilemma problem, the shadow of the future probably isn't going to get us to that happy equilibrium. Then I floated the idea that in many cases, we don't actually have a clear time horizon. Maybe I'll see you again, maybe I won't. The probability can be high, the probability can be low, but in the real world, time horizons aren't necessarily that certain, and that fact opens up the possibility of cooperation. On Thursday, we had to take a little interlude to talk about comparing rewards in the future versus temptations in the present. That's essentially the problem in the repeated prisoner's dilemma. And we saw how to use discount factors to do that. So now today I'm going to go back to the main narrative. Okay? If we're in a situation where we are playing a prisoner's dilemma repeatedly, and we're not sure how long this interaction is going to go on, okay, can the possibility of future reward for cooperation get us to make cooperative choices in the short run? Okay, can the shadow of the future bring about cooperation? Can the possibility of, if I've been a good guy to you, you'll be a good guy to me, can that get me to overcome the dominant strategy I have to defect in the short term? Okay, so I think you guys have already figured out the answer to that is sometimes, and the main thing we're going to do this week is elaborate on just what we mean by sometimes. When can the shadow of the future be enough to support cooperation? Okay, so what we need to do now is we need to go back to some basics of game theory. Now we're in this world of a repeated game which is different than a sequential game with lots of steps. Remember, I talked about this last week. We're in fine shape for analyzing sequential games with lots of steps where we have lots of moves and counter moves till we finally get to a payoff. You guys knew how to do that before the midterm. We just solve it with rollback. Now we've got a different story. Now we've got a game that's repeated over and over again, and what this means is we choose our strategies, we get our payoffs, then we interact again, okay, and again, and we're not sure how long our interaction is going to be. We're going to be focusing on indefinite time horizons throughout this week. Okay. What this means is we play our prisoner's dilemma, we get our payoffs. Maybe it's the punishment payoff because we both played our short-run dominant strategy. Maybe it's the reward payoff because we both cooperated. Maybe I got the sucker payoff because I cooperated and you defected. Maybe vice versa. We got that payoff, and then when we go to the next round, we remember what happened in the game before. That's the big difference between a repeated game and a sequential game that just has a lot of moves. In repeated games, you get the payoffs, then you make more choices. Okay, so it's starting to sound more like real life than any of the games that we've done so far. Okay. So what it means for strategies is that strategies in repeated games can be a lot to manage. Okay? If I'm saying we're playing a repeated prisoner's dilemma with an indefinite time horizon, my strategy has to tell me what to do at any point in the game for any history. Okay? So my strategy has to tell me what to do the first time we play each other. Then my strategy has to tell me what to do the second time if you cooperated, the second time if you defected. Then my strategy has to tell me what to do in the third round, given all the possible moves that have gone before in the second round. Okay, so just the set of strategies for a repeated game is a lot to manage. I'm never going to ask you something like write down all of a player's strategies in a repeated game because you wouldn't be able to do it. Okay? That's something I asked you about regular sequential games where the payoffs happened just once. Okay, so we're just going to have to accept that fact that we're not going to be able to think about all the strategies in a repeated game, but we could think about some. Okay, and I'm just really trying to emphasize this at the beginning because it's different than what we've done so far. So far I've been, I think, very thorough, and you think about every possible strategy, and the strategy is in equilibrium if given the other person's strategy there is no alternative that could have given you a higher payoff. You're very clear about comparing each strategy to every other alternative. We are still going to do that, but we're going to have to be creative in finding ways to group this infinite number of strategies. Okay? Okay. So what we're going to do is we're going to think about one possible strategy in the repeated prisoner's dilemma, and it's a famous strategy. It's called the Grimm trigger strategy. So I'm going to just write up here what the Grimm trigger strategy is. Cooperate as long as no one has defected in the past. If anyone has ever defected, then defect. Okay. So this is a contingent strategy. Okay? This short little strategy can tell me what to do in any repeated prisoner's dilemma at any point in the game. Okay? Because this strategy is kind of divided up all the possible histories that a repeated prisoner's dilemma can give rise to, and there's lots and lots of them, and organize them into two groups. Okay? Either we're in a situation where everybody's been good all the time. I've always cooperated, you've always cooperated. Nobody has ever defected. Either we're in that situation or we're not. Okay? If we're in this good situation, what Grimm trigger says is, if nobody's ever defected, if you've been good to me and I've been good to you, I'm going to cooperate. Okay? That's the good part of Grimm trigger. The grim part, the reason why it's called, sometimes it's just even called the Grimm strategy, is there's no forgiveness in Grimm trigger. Okay? You defect against me once, I will never, ever, ever forgive you. I'm going to defect against you anytime I interact with you. There is no possibility of ever making amends. Okay? So the idea behind the trigger part is one defection triggers punishment. Okay? And it is grim because there is no forgiving, no forgetting. Okay. All right. So now what we want to ask is, if both players play Grimm trigger in a repeated prisoner's dilemma, is that a Nash equilibrium? Okay. When we're asking ourselves, can these people cooperate? Can these people overcome their short-term incentive to defect, to do something that helps them but hurts the group as a whole? What we're asking is whether Grimm trigger is in equilibrium or not. Okay? It's always a strategy. It's always something that you can do. The question is, if your partner is playing Grimm trigger, are you glad that you played it, or do you wish you'd done something different? Okay, that's the answer. That's the question that's going to have sometimes a yes answer, sometimes a no answer. If the answer is yes, I'm glad when you play Grimm trigger, I'm glad that I'm playing it too, then we're in equilibrium. Okay? If the answer is when you're playing Grimm trigger, can I do better by doing something else, then we're not in equilibrium. Okay? All right. So now to answer that question, to apply our Nash equilibrium logic, the logic that we've been using ever since the midterm and really in mostly before the midterm as well. In order to do that, now we need to have a specific prisoner's dilemma up here with numbers that I can actually compare. So that's where we're going to go now. So what I'm going to do now is I'm going to write down the stage game. And just again, recalling from last week, the stage game is the thing that we're repeating. Each round in the repeated game means playing this game and getting the payoffs once. And then we go on to the next round and we play the stage game again, and again we get the payoffs. Okay, so I'm using the slack off, work hard version of the prisoner's dilemma, the one that we were working on last Tuesday. Got player A controlling the rows, player B controlling the columns. They have the same choices, slack off, work hard. When they both slack off, their payoffs are 0. When they both work hard, their payoffs are higher. They get payoffs of 3. If I work hard and you slack off, I get the low sucker payoff of -2, and you get the high temptation payoff of 5. So you like that, and I feel bad about it. And when the roles are reversed, the payoffs are reversed. When I'm the slacker who's free riding on you, I get a high payoff, and you get the low sucker payoff. Okay, so I'm pretty sure those are the same numbers I was using last week. If we play the stage game just once, slacking off is a dominant strategy. It is a prisoner's dilemma. This would be the only Nash equilibrium in a single shot game. Okay. In the repeated game, though, we're not just saying, would you do better in this round by slacking off than working hard? We're saying, would you do better now and in the future? Would your total stream of payoffs, what you're getting now and what you're going to get in the future, would it be better if you slacked off, or would it be better if you stuck to this strategy? Okay? So when we do the Nash equilibrium calculation, when we do that kind of analysis for a repeated game, we're thinking about short-term and long-term consequences. So we're thinking not just about the higher payoffs this time, but lower payoffs in the future, because my behavior now is going to affect the way the person I'm playing with is going to treat me in the future. Okay? So that's what we have to be able to do. And what I'm going to do here is I'm going to do a supplementary table here that will just show the moves and the payoffs that one player gets from playing Grim Trigger versus doing other strategies. And in that table, I'm going to hold the other player's strategy constant. Okay? So let's just get that going up here. Player A's payoffs. Started to write from Grim Trigger there. Let me not say that, because I'm going to look at player A's payoffs from different strategies in this table. Okay. Or am I? No, I think I am going to separate this just from Grim Trigger here, from Grim Trigger. And I'll do a different table for other strategies. Okay. All right. So what I need to do now is I need to account for what's going to happen in various rounds. I don't know how many rounds there's going to be. I think by the time we get out to the 4th round, you'll see the pattern here. Okay. And we're going to have player A's action. We're going to also in this table have player B's action, and we're going to have player A's payoff. Okay. Right. Yeah, that's how I want to do it. Okay. So this is player A in this table. This table is going to show the actions and the payoffs from playing Grim Trigger. Okay. In the very first round of this game, you guys look over there at the blue. There's the Grim Trigger strategy. I'm player A. What am I going to do in the first round? What am I going to do? I'm going to cooperate. Okay? Grim Trigger says cooperate as long as no one has defected in the past. Well, it's the first round. No one's had a chance to defect. Okay? So in Grim Trigger, you start off nice. No one's defected. I am cooperating. Okay? Now you might have been wondering why in a table about player A, I needed to put in player B's action. And the answer is, I need to know player B's action in order to get player A's payoff, right? That's what makes it a game. Okay, so I need to add something to the table. We're going to put B in green here. We're going to assume B plays Grim Trigger also. Okay? And to get a sense of where we're going with this, I'm going to do another table where A does something different here, but B is still going to do Grim Trigger. Okay? That's the Nash equilibrium comparison there. Okay? So B's playing Grim Trigger in this table, same as A, so B is also going to cooperate. What's A's payoff? 3. That's good. Okay? Round 2. I'm player A. I'm playing Grim Trigger. In round 1, I cooperated, B cooperated, I got 3. What do I do now? Cooperate. What does B do now? Cooperate. This is where we want to be. What's my payoff? 3. Okay? As long as we're both playing Grim Trigger, I'm going to take the liberty of filling in a few more here. As long as we're both playing Grim Trigger, all we're ever going to see is cooperation on the equilibrium path. Okay? So for all the mean name of Grim Trigger strategy, the outcome of both players playing Grim Trigger is a happy story. Okay? Grim Trigger, good. Everybody cooperating, high payoffs here. All right. So now, let's make the other table over here, where, again, the table is going to focus on player A's payoffs from I'm going to call it alternative strategy number 1 here. Okay? Which I haven't said what it is yet. I will say it in a minute. But it's going to be something different, and I bet you guys can guess what it is. We're still going to assume that B plays Grim Trigger. Okay? And we're going to do the same thing. Okay? We're going to look at A's action from this alternative strategy, B's action from Grim Trigger, A's payoff here in round 1, in round 2, up to round 4, and we'll see if we are getting the picture then. Okay. What would be an alternative strategy that A could play here? What would be an alternative? What would be something that might tempt A away from Grim Trigger? Just defect. I think I heard that. Okay? An alternative strategy, we'll write it in, I think we'll keep strategies in blue, here. Okay, so here's Grim Trigger. Alternative strategy number 1 is always defect. Okay? That's something I could do, right? Go with my short-term incentive every time. It's not the only other thing I could do, but if this strategy gives me a higher stream of payoffs when my opponent is playing Grim Trigger, then Grim Trigger is not going to be in equilibrium. Okay? Because then, if my partner is playing Grim Trigger, if this strategy gives me higher payoffs, I'm going to play it. All right. So, alternative strategy is just always defect. Okay, so that's an even simpler strategy than Grim Trigger. It's telling me I'm just a bad guy. I do what's good for me in every round. Okay. B is playing Grim Trigger. What does B do in the first round? B cooperates, right? In the first round, nothing's happened. B is following the Grim Trigger strategy. The Grim Trigger strategy says nobody's defected. You try to do the right thing. Okay? Everybody see this? I'm varying A's strategy here, but I'm still assuming that B is playing Grim Trigger. Okay. What's A's payoff from that? Sucker, says A. I get 5. Isn't that good? Okay, in round 2, I'm B. I'm playing Grim Trigger. What am I going to do? Defect. I'm done with you. You betrayed me once. Am I ever going to forgive you? Am I ever going to cooperate with you again? No. That's what Grim Trigger tells me. What's A's payoff here? Okay. So now what we want to do is, what we want to look at is the overall value of these two strategies. This strategy, playing Grim Trigger, when my opponent is playing Grim Trigger, is going to give me 3 in this round, 3 one round in the future, 3 2 rounds in the future, 3 rounds in the future. But remember, I'm sort of uncertain about when our time horizon is. I might not even get to 3 rounds in the future. For all I know, I might not even get to the next round, right? This is back to the anybody can be hit by a bus thing. Okay? So what I need to do is I need to find some way to look at the set of payoffs that are going to occur at different points in time and put them all on a scale that we can compare to something I'm going to get right now. Okay, so what I need to do is I need to find the present value to player A of, I'm going to just abbreviate it GT, okay? Okay. When I'm writing this at the bottom of the table, it's the present value to player A of playing Grim Trigger, given that B is also playing it, right? You can't assign payoffs unless you know what both players are doing. Okay, so the present value to me of playing Grim Trigger when my partner is playing it is going to be 3 today plus, what do I need to do to this? Am I sure I'm going to get this? No, I'm not. Okay. Is it worth absolutely 3 to me? It's worth a little bit less. I need to discount it. Okay, I need to use the discount factor like we were doing in class on Thursday because I'm not sure. I think that we're going to interact again. I think I'm going to see you again. I think you'll have a chance to reward me for the fact that I was good this time, but nobody can be perfectly sure. So I need to multiply that 3 by the discount factor, by this number that's between 0 and 1. When it's close to 0, it's telling me that the future does not loom very large to me. Okay, it's telling me that those future rewards are not very big. Okay? I don't think that my probability of getting to the next round is very high, or I'm just a very impatient person. As delta becomes close to 1, I'm becoming a more patient person. The future is really important to me. I think it's really likely that I'm going to interact with player B again. Okay? But no matter what, delta is less than 1, and that future reward is not quite worth as much as to me as the 3 I'm getting right now. Okay? There's always some uncertainty. Of course, it's not just 1 round in the future. Maybe I'll see player B 2 rounds in the future as well. Okay? Now there's even more uncertainty and more having to wait there. So I discount that twice. Again, just like we were doing at the end of class on Thursday. I discount this 3 times. Okay? I'm kind of gotten out of the range of the columns here, but not out of the range of the potential interaction. This could go on and go on up here to very high values of delta to some high power times 3. Okay. So that's looking a little bit weird. Okay, here we are, and we're not done yet. Okay, there's no definite end to this interaction, so there's no definite end to this sum here. Okay. That's looking bad, but we're going to solve this problem. Don't worry. We're not going to really have to calculate an infinite, do an infinite number of calculations here. We've got a shortcut for that. Okay. Before I talk about how to evaluate this infinite sum here, let's just do the same thing over here. Let's figure out the value of always defect. So this is the present value to player A of, I'm going to call this, I'm just going to write it out, always defect. Again, this is given that B is playing Grim Trigger. Okay. Well, this one's easy. Okay. It's 5. I'm going to get 5 right now, and I'm going to get 0 every round in the future because you're going to be punishing me forever, no matter what. So there's no concern about adding up an infinite number of terms over here. Okay. So what we need to know over here is the present value to A of playing Grim Trigger greater than or equal to the present value to A of always defect. Okay? If yes, then A does not regret playing Grim Trigger, as long as B plays Grim Trigger. I'm not repeating as long as B plays Grim Trigger every time, but it's always in there. Yes? The question is if the payoffs for slacking off here were 1 instead of 0, which they could be. It would still be a prisoner's dilemma. And then we would have 1s here. Then you're exactly right. Then we would have an infinite sum here as well. Okay? And you're going to see that that's going to be fine. Okay? For this example, I'm making it as simple as possible, but you'll be able to handle that case in about 20 minutes. Okay? Okay. So if we had non-zero numbers here, it would be 5 plus delta times 1 plus delta squared times 1, etc. If the payoff here was 2, it would still be a prisoner's dilemma. It would be 5 plus 2 times delta, 2 times delta squared plus 2 times delta cubed, whole thing. The overall thing we're doing is we're comparing an infinite stream of payoffs from the potential equilibrium strategy. Okay? The potential equilibrium strategy is Grimm trigger. That's the one we're focusing on. We're comparing it to other things that the players could do in the game. And in both cases, we're looking at the present value, the stream of payoffs over all the periods, but appropriately discounted so that we can compare benefits that are occurring at different points in time. All right. So there's just this little technical issue right now that's preventing us from plugging this on one side of an inequality, plugging this on the other, and solving it the way we've always done before. And the little technical issue is, what do we do with this sum that never ends? Okay, so here we've got math to the rescue. Okay. There's a formula that I'm going to show you in 1 second that will allow us to evaluate this geometric sum. Okay, so let's do a little interlude on geometric sums, what they are and what they add up to. Well, this is one. This is a geometric sum. The simplest geometric sum looks like this. 1 plus delta to the first, delta to the second, delta to the cubed, going on forever in this pattern. Okay. The way you may well have seen it written before is using summation notation. So let me just write the same thing here. It is the sum as I goes from 0 to infinity of delta to the power I. Okay. Now I know these summation symbols, people don't like them, right? In many, many classes, people will do fine. You're doing some math on the board. You put the summation symbol up, and people don't like them. I think I know why people don't like these symbols. They're very dense. There's a lot of information in this kind of symbol. Okay? So in this class or in any others, when you see something like a summation symbol, instead of thinking, oh, there's that confusing thing again that I get wrong all the time, just take a deep breath and remember that it's confusing because there's a lot of parts, and think about the parts as individuals. Okay, so let's go through what the individual parts of the summation symbol mean. Okay, so the big symbol here is a Greek letter sigma, same thing that some of the fraternities have on the outside of their buildings. It is in fact the letter that in Greek makes the S sound, and S is for sum. Okay, sigma, S, sum. And it's telling you that this is a sum with a pattern in it. The pattern is what's in front of the sum. Okay? Part of the pattern is changing, and that part, the part that is changing, appears above and below. Okay? So just writing this out in words, this is, I said it before, I'm going to write it though. The sum as I goes from 0 to infinity of delta, really be, write everything out, to the ith power. Okay. So one thing you can do if you see these symbols and you're unhappy about them, you're feeling lost, is just try to read them out loud in English and expect it to take some time. Okay? Just literally reading the symbol out loud will often help you see what it means. Another thing you can do, if this probably wouldn't happen in Poli-Sci 30, but it may well happen in other classes. These symbols are used a lot in statistics classes. If you see a summation symbol, and again, you're not sure what it means, and yes, you've read it out loud, and it's still looking a little fuzzy, write it out this way. Okay? This takes more time to do. It's kind of tedious. It's kind of ugly with dot, 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 and so on going off to the end. But looking at this, you can see a pattern that's just left implicit here. Okay. All right. So that's some thoughts on summation symbols. Getting back to my main argument now, I can have all sorts of things here. I can add up, this would be a different summation, I from 0 to infinity I. This would just be sum of the numbers beginning with the integers beginning with 0 and going up to infinity. That's a sum, but not a geometric sum. A geometric sum has exactly this pattern. It says you're taking some base number, raising it to higher and higher powers, and adding them all up. Okay? One other thing to notice about this is that the sum starts at 0. You may have forgotten something that I know you guys all learned at one point. You may have forgotten the fact that any number raised to the power 0 is not 0, it's 1. Okay, so this 1 right here is your delta to the 0 power. Okay. So this is I equals 0, I equals 1, I equals 2, I equals 3. We go on and on and on and on, and we never stop. These are alternative ways of writing and talking about geometric sums. All right. So why am I making a big deal of it right now? We've got one right here. Okay? The very thing that we're trying to evaluate, that we're trying to compare to something else, look, I can factor out the 3. Okay, I'm getting the 3 in every round, and let me keep using blue there. What am I getting? I'm getting 3 times 1 plus delta squared plus delta cubed, and so on. Okay? So this is the number 3 times this geometric sum. Okay? So that's one reason why I'm belaboring it. The other reason why I'm belaboring it is that we actually have a formula for this infinite sum under some circumstances, and the circumstances are good ones for us. So this geometric sum equals 1 over 1 minus delta whenever delta is between 0 and 1. Well, how lucky can we get? Those are exactly the cases we care about here. Exactly the set of cases that make sense for us. When delta is a number between 0 and 1, that is the case where this fact about the geometric sum can help us. Okay? So how can this be? How can this be that we're adding up an infinite number of things, but the sum is still going to be a finite number? The way it works out is that when delta is between 0 and 1, and we're raising delta to higher and higher powers, these powers of delta are getting smaller and smaller. Okay? So yes, we're adding an infinite number of things, but each successive term in the sum is smaller and smaller, and sometimes when that happens, the sum, what you hear in a math course, converges. Okay? When the geometric series converges, this is what it's equal to, and the conditions under which it converges are precisely the ones that we care about, delta being between 0 and 1. Okay? When I'm writing this on the board and saying that it's a fact, what I'm kind of telling you guys is I'm not like proving this to you. Okay, I'm trying to give you some sense of why it might not be true. Depending on kind of the level of the calculus course that most of you guys have taken, you might have proved it in that class. If you take a real analysis class, you'll prove all sorts of things like this. So It is logically valid. Poli-sci 30, we're not doing the proof. We're just accepting that it is true, and this is going to be very helpful to us. Okay? Last thing I will say about this is I think by the time you're done with this week's homework, most of you guys are going to have it committed to memory. That said, some people remember things better than others. Every year goes by, I remember things worse than I used to, so I'm sympathetic to not being good at remembering things. So if you need to use this on the exam, I will put the formula on the exam. Okay? If that's a hard thing for you to stick in your memory, that's okay. It'll be on the exam. What will not be on the exam is detailed instructions about how to use it. That's what you guys are responsible for internalizing. Okay. All right. So now we've got this fact. And now we can go back to, I think what I'm going to do is the same thing I just said. I'm just going to copy the fact over here. The sum as I goes from 0 to infinity of delta to the I power is 1 over 1 minus delta whenever delta is between 0 and 1. Okay? We can use this because now we can apply it right here. Okay? We can apply it to the present value of playing Grim Trigger when your opponent is playing Grim Trigger. Okay. So this is what we need to know. I'm going to erase the reason why we need to know it. We'll come back to that. And we're just going over here to say that the present value to player A of playing Grim Trigger is 3. I'm looking right over here. It's that 3 payoff I'm going to get in each round, multiplied by this geometric sum that tells me how to discount rewards that are happening further and further in the future. Okay, so this geometric sum is doing a lot. It's the first period, no discounting. In the next period, I discount by 1. After that, discount by 2, etc. All the way off toward this infinite horizon, that the geometric sum formula tells me that is 3 multiplied by 1 over 1 minus delta. It's just a fact. Very nice fact. Very convenient fact for us in trying to figure out whether Grim Trigger is in equilibrium. Okay? In this case, the present value of always defect didn't require a geometric sum. It's just 5, but as the person in the back pointed out, there could be cases, and we will see cases this week, where we have to apply the geometric sum formula on both sides. Okay? But now here we have 2 things that we can very nicely, very easily compare to each other. Okay? So I'm going to leave those tables up. Anybody want to ask anything about this before I erase? Okay. It's kind of a lot of wind up. I hope you're seeing that the application of that formula is really easy. Okay, you see the geometric sum pattern. You just plug in 1 over 1 minus delta. So great. All right. So getting back to what we want to know, the present value of Grim Trigger is at least as good as the present value of always defect. What does that mean? It means that 3 over 1 minus delta is greater than or equal to 5. Okay? So what we're going to do now is something we've done all along. We're going to solve this inequality for a threshold value of delta. Okay? We did this when we looked at variables in sequential games, when we looked for the minimum or maximum probability that would make a certain choice the optimal one. We're going to do the same thing here, but we're going to be looking for some threshold value of the discount factor. How patient do we have to be to make Grimm trigger an equilibrium? That's what the question is going to come down to. Okay? So we're going to multiply both sides by 1 over 1 minus delta. When we're working with inequalities, we always have to remember the business about when we multiply by a negative number, switching it, but that's not applying here because we know that delta is between 0 and 1. I'm emphasizing that because if you forget that delta is between 0 and 1, if you just kind of focus in on the symbols, things will get very hard. If you remember that delta is a discount factor, it's like a probability. You only have to think about values greater than 0, less than 1. Things are easier. Okay, so we're multiplying by a positive number. We get 3 greater than or equal to 5, 1 minus delta. Okay, multiplying through by the 5 here. I'll just do it. 5 minus 5. Delta, I'll bring this over to this side, this over to that. 5 delta greater than or equal to 2. Okay. What is this saying? Delta greater than or equal to 2/5. If I'm player A and the promise of $1 tomorrow, $1 in the next round, is worth at least 40 cents to me, then I would rather play Grimm trigger than always defect. $1 tomorrow being worth 40 cents today, that's not a real stringent requirement. I don't have to be extremely super duper patient to say, yeah, $1 tomorrow is worth at least 40 cents today. Okay, so this is the 2/5 is the minimum value of the discount factor for which player A would rather play Grimm trigger than always defect. Okay, so that's good news. That is very good news. And I think before I talk about asymmetric payoffs, I want to say a little bit more about what the Nash equilibrium calculation is here. Okay, I haven't quite gone as far to say that when delta is greater than or equal to 2/5, that mutual Grimm trigger is in equilibrium. I haven't quite said that, but it is in fact true, and I've almost shown you everything you need. Okay? What I've shown, strictly speaking, is that as long as delta is at least 40%, okay, as long as the penalty you pay for waiting is at least, or is not, the penalty, I'm saying it the wrong way, the penalty is not worse than giving you 40% of the future value today. As long as that's true, if your partner is playing Grimm trigger, you won't want to deviate to this alternative strategy. In order for it to be a Nash equilibrium, though, we have to say you don't want to deviate to any alternative strategy. Okay? We haven't quite gone that far yet. So let's go that far right now. Can any of you guys think of another different strategy, another thing that player A could do different than always defect that would be better for her, that would be a more tempting way to deviate from Grimm trigger? okay, that would give her a higher stream of payoffs than what she gets from always defect. Yes, Elaine.
Could she like cooperate and then defect in the last period?
Yeah, okay, so one thing Elaine is thinking of is cooperate for a while and then defect. Okay, so one thing that wouldn't make sense, I'm just going to elaborate a little bit here, would be cooperate for a while and defect in the last period. You can't do that in this game because you never know when the last period is. Okay, but one thing you could do is, we're going to do a, okay, we're going to do it on this board. We're going to do the same table with that idea. So another way that you could deviate from grim trigger would be to cooperate for a while, to lull your partner into thinking that you're really a good guy, and then defect. Then get that sucker payoff. Okay. So this is going to be player A's payoffs from, and what I'm just, I think to give the flavor of it, I'm going to say cooperate for 2 rounds, then defect. Okay. As before, as throughout this, we're holding B's behavior constant, like we've always done when we think about Nash equilibrium. Okay, so B plays grim trigger, and we have round 1, 2, 3, 4. We have A's action, B's action, A's payoff. Okay. So B's playing grim trigger, I'm playing A. I'm thinking of other things I could do, wondering if any of these alternative strategies would give me a higher stream of payoffs. Okay? So I can cooperate for 2 rounds, then defect. So this strategy, it's pretty easy to map what this strategy is telling me to do into these actions. It says cooperate here, then defect, and it doesn't actually say what to do after that. I'm going to say defect forever. We could think about the alternative of then going back to something else. What's B's action in the first round? Cooperate. Second round? Cooperate. Third round? Cooperate. Fourth round? Defect. That did it, player A. We're history. Okay, I'm going to defect against you again and defect against you forever into the future. So A's payoff here, 3. Good. 3 again. 5. Oh, yeah, we like that. Okay, here. 0, 0, 0, 0. Okay. So what this is giving us, this is a good example because it shows yet another form that the present value calculations can take. And they're all applying the same basic idea. Here we had non-zero payoffs in every period, so we had to use the geometric sum to calculate our present value. Here we had a payoff that wasn't 0 in the very first round and then zeros after that, so we didn't have to worry about discounting. There's no future payoffs here. Here we have, blue's my present value color today, so let me get blue. The present value to A of, we're going to call this what? CCD, cooperate, defect. That's just a name I'm giving to this alternate strategy. Is going to be, I get 3 in this round. I get that 3 in round 2. Okay, but I've got a discount because we don't really know if I'll get to round 2. We don't know if I get to round 3 either, but if I do, that's when I pounce. Okay, take her by surprise, get the 5, and then 0. thereafter. Okay. Okay, so that's not obviously worse strategy than this one. Indeed, it might actually be higher, might not. So let's look. What we're going to do now is we're going to compare this way of deviating from Grimm trigger to Grimm trigger. Okay? Theoretically, what we would have to do is compare every single thing we can think of, but what we're going to see is that the different things to do are going to fall into categories. Okay? So let's finish with that. Is the present value to A of CCD actually, let me just write it exactly the same way I did before. Before I put Grimm trigger first, so let me do it that way. Present value to A of Grimm trigger greater than or equal to the present value to A of this cooperate defect strategy. If that's not true, then we know Grimm trigger is not in equilibrium. We know the present value of Grimm trigger, this is 3 over 1 minus delta. Okay. And the question is that greater than or equal to 3 plus delta 3 plus delta squared over 5. Okay. Okay. Watch how I do this. Watch how I first correct my inequality. What I'm looking at here is something that looks like the start of a geometric sum, right? There's the delta equals 0, delta equals 1 term, and then it's not a geometric sum anymore. Okay? So here I'm going to use that geometric sum formula in reverse. Okay? It seems like this formula would only be convenient going this way, but sometimes it's convenient to expand it out the other way. Okay? Another way to think about it is, suppose I hadn't done this step. Suppose I just had the present value to A written out like this. 3 plus 3 delta plus 3 delta squared, 3 delta cubed, etc. The question is that greater than 3 plus delta 3 plus delta squared 5? Okay, no dot, dot, dot here. Okay, this is a finite sum because we start getting zeros. Why did I do it this way? I did it this way because the payoffs in the first 2 rounds from this different strategy, this cooperate defect strategy, in the first 2 rounds it gives me the same payoffs as Grimm trigger. Okay, right? In these first 2 rounds, another way to think about it is you couldn't tell in the first 2 rounds whether player A was playing Grimm trigger or playing this alternate strategy. The payoffs are exactly the same, so let's just get rid of them. They're on both sides of the inequality. Okay, so then our question is whether 3 delta squared plus delta cubed, going on and on forever, whether that is greater than delta squared 5. Okay, so that's looking a little bit trickier. That doesn't exactly fit our geometric sum pattern, so let's do a little work on it to get to something that may or may not fit this. Okay, one thing I'm going to do is I'm going to notice that once I've canceled out the terms that appear on both sides, every term here, every term in this infinite sum and this delta squared 5 here has at least a delta squared. So I'm going to factor that out. Okay, that's going to write it here. Factoring out delta squared leaves me with 3 plus 3 delta. Let me just keep the pattern clear here. We could have written 3 delta to the 4th here. It doesn't matter how many terms I write before I start doing the ellipsis. This dot, dot, dot always means that there's an infinite number of terms. And once I've factored out delta squared, here's my 3 delta plus 3 delta squared. Now I'm going to put in my dot, dot, dot. That has to be greater than or equal to 5. You guys are thinking, where's she going with this? Maybe you see at this point where I've gone with it. Now I do have my geometric sum. Okay, and this is something that anytime you're working with geometric sum formula, sometimes it's really easy. Sometimes it's as easy as it was in our first comparison, where the formula for the geometric sum just pops right out at you. Okay, it's exactly there. Other times you have to do a little bit of work. Okay, and the two things that I did here will almost always get you what you need. Subtracting off common terms and factoring out common terms. Yes? This one here, this one is a delta squared. So what I'm doing here is I'm factoring out the delta squared. So factoring out this delta squared leaves me just the 3. Yeah, it didn't line up very well, but this is my delta to the 4th power 1 with 2 of them factored out, and similarly over here. Okay, so now I have over here 3, 1 plus delta, all that. When is that greater than or equal to 5? Well, that's exactly what we did before, right? This is going to be true exactly when the present value of Grimm trigger is better than the present value of always defect. And if you look at the pattern of payoffs and actions, you'll see why. Okay? Once we get to this point in the game, it's a game with an infinite horizon. So we get to this point, it's just like the stream of payoffs are just like what would be starting at the beginning. The only thing that's different is the history. Once we get to this point in the game, it's just like Grimm trigger. Okay? So waiting for 2 rounds to defect will be a good idea under exactly the same conditions that defecting at the outset would be. Okay, a way to think about it is that if it's worth your while to defect in round 3 after cooperating 2 times, it would have been worth your while to defect right here. Okay, because from this point forward, the games are exactly the same. Okay, so a generalization, and actually it's the generalization that Elaine used when she brought up this alternative, is that the condition for defecting after some number of rounds is exactly the same as the condition for defecting in round 1. Okay? So that's big. We've ruled out a whole lot of alternative strategies here. Okay? And I hope this makes intuitive sense, right? If after having played the game for a while, you think it's worthwhile to get this one-time gain, okay, to take advantage of your partner in the short run, knowing that you're going to be punished in the future, if that's worth your while in round 3, it would have been worth your while in round 1 too. Okay? So yes, sometimes this strategy will be a better one than Grimm trigger, but it's under exactly the same circumstances that defecting right from the beginning would have been as well. Okay? Okay. So there's one other thing that you could do differently in Grimm trigger, that one other form of a strategy that you might think would be tempting for players. We'll talk about that on Thursday. Okay, but we're almost done with that.